Right. Good evening, everyone. So this is our this is our third day school. So you have faced your first CAT examination, right? So I'm very disappointed. Your answers
Madam, can we get our result before CAT 2?
yes, we'll definitely send you, right? So the CAT 1 marks, don't believe that you have very good marks for CAT 1 because your answers are very poor. You have answered very little, very little marks you will get, right? So get ready for the second CAT, right? Otherwise, you will ended up with very low OCAM mark, right? So get ready for the second CAT very well, right? Give me 1 second. Right. So, so you all know for the second CAT, what are the content to be covered?
Basic.
So, huh?
Unit 3 and 4.
Unit 3 and 4, that is electrochemistry and phase equilibria, right? So, your first CAT, why didn't you study properly? So, is it hard for you all? Unit 1 and 2, what was happened? You tell me truth, you didn't study, or is it hard for you to study? Huh? What was the reason you have answered very, poorly in CAT 1? Is it because you didn't study? Because the paper is not that hard. Is it hard for everyone? CAT 1 paper?
No, ma'am.
Then why didn't you? Most of y'all have answered very poorly, right? So, that therefore, you get ready for the second CAT, right? So, which will be on 11th October, right? So you will get any type of question paper. So get ready for any thing, any model can be there in the question paper, right? Okay, so you will have to. I will cover in this day school unit 4. Can everyone here see my screen?
Yes, ma'am.
Yes, ma'am.
Right. So let's start. Okay. So this is your yes. You wanted to say something? Do you have anything to clarify? Okay, so let's start. So this is your unit 4. So you all know you have to study all 6 sessions in unit 3 as well as all 6 sessions in unit 4 for the second CAT, right? So start now itself. You will have less than 1 month time, right? So you have to study this very well, right? So this phase equilibria, right? Unit 4, try to get the basic into your mind because this will be applicable when you come to level 5 or even higher levels if you are get selected for special degree, right? So, and even if you are going to do a research based on something like this, you will have to know the basics of the phase equilibria, right? Okay, so let's first see a brief introduction to phase equilibria. So, what is a phase? I have covered few of these the basic things during your compulsory day school. Can you all remember? What is a phase? Hurry up quickly. Huh? What is a phase? A phase, it is a part of a system, right? Which is uniform throughout the chemical composition and physical properties, right? So we call it as it is homogeneous and separated from other homogeneous parts. So let's see, you have a beaker of beaker. You have water in this beaker. You have put an ice cube into this, right? So now here at the beginning you have, so what are the two phases you have here?
True. Liquid
Yeah, you
and
have
solid.
two phases, the solid phase and the liquid phase, right? So these are having uniform throughout the, so this solid until it's dissolving, it's uniform throughout the chemical composition. When it the composition of the phase is uniform and its physical properties are also homogeneous. Separated from liquid, it's another type of phase, right? For example, ice and water, where the separation between phases is quite clear. Here the solid ice and water liquid are two phases of water, right? So that is called the phase. Phase is a uniform system throughout the chemical composition and physical properties, right? So the phase diagram is really a map. It's a map that shows the conditions under which the various phases exist. So why do we need to study about the phase diagram? That is because it is a map of, it's a map which shows you the condition under which the various phases exist. So you, by looking at the phase diagram, suppose it's a solid liquid phase diagram, right? So by looking at this diagram, we can see what sort of phases are in this under at this temperature, and the what is the mole fraction of particular compound, right? So by looking at this, it's actually a map, right? So by looking at the phase diagram, we can say what sort of phases, the various phases that are thermodynamically stable. What is thermodynamic and kinetics? What do we, if the system is thermodynamically stable, what is its delta G? Hmm? If the system is thermodynamically stable, huh?
Delta G is 0.
No, not zero.
Minus.
It should be a
Less
negative
than 0.
wave. It should be a negative delta G. Then the system exists thermodynamically stable manner, right? Okay. So let's move forward. Right. So this is a phase diagram. This is a typical phase diagram for one component system. So what is the component? Huh? So for example, the phase diagram is basically that present the domains of stability, right? So by looking at this phase diagram, so you have how many, so this is one component system, the typical phase diagram for a one component system. Suppose this is for water, right? The phase diagram for water. So what is the component you have here?
Water.
Water is the component. So you have only water in this system, right? However, how many phases does it exist?
Three
Here
phases.
Three phases.
Three
phases.
phases.
Can be
Three
solid,
phases.
liquid, and vapor phase, right? So these are the phases which can exist. So you all know at certain temperature and pressure, right? So let's see if you are going to keep the, keeping the pressure constant. Suppose you are somewhere here, right? So what will happen when we increase the temperature? Keeping the pressure constant, when we increase the temperature, so initially you have solid phase, right? So let me use this, right? Somewhere here, right? So you have a constant pressure here. So now suppose you are somewhere here. So what is the phase you have here? This domain
Solid.
only solid, right? So you're keeping the pressure constant, increasing the temperature parallel to x-axis. So at this point, you can observe a first solid gas particle appear, right? So what is this temperature? Solid to gas equilibrium?
0
Huh?
degrees.
මොකද අපි ඒකට කියන්නේ?
Vaporization.
Solid to vapor equilibrium?
Sublimation.
Very good. Sublimation, right? So you can get an idea at which temperature this occurs under the constant pressure of this. This is the sublimation temperature. So now let's see, you are going to keep the temperature constant and increase the pressure. So what will happen? Initially you have gas phase. You have here all the gas phase, right? This domain. So you increase the pressure, keeping temperature constant. At this temperature, what will happen? The first liquid particle appears, right? So that is gas to liquid equilibrium, right? So in other way, suppose you are somewhere here, right? You have only liquid, right? So keeping the temperature constant, you dropping the pressure. You are at this point, what will happen? At this point,
Liquid to gas
First
equilibrium.
gas particle.
yes, first gas particle appears. So after that, you have only gas phase, right? So this is liquid to vapor equilibrium. So what is that temperature? What we call this as? This equilibrium.
Condensation.
Vaporization.
Yes, that is vaporization, right? So by looking at this type of map, you can get an idea what sort of equilibrium occurs between phases and what are the conditions at which temperature this gets sublimated, right? So like that, wise, the phase diagram is basically a presenting the domains of the stability, right? So these are the domains. You have liquid domain and gaseous domain and solid domain, right? And the limits of stability. So what are the limits? So here this is a limit, right? So liquid gas equilibrium. What we call this as? Liquid gas equilibrium? Huh? That is vaporization, right? And solid liquid equilibrium? This one? This is again another limits of stability, right? So these three are the limits of stability. And reading a map will tell you when it comes to the equilibrium, right? So by looking at the phase diagram, you can say what phases are present, right? So here you have only liquid. At this limit, you have both liquid and gaseous. And the second point is the states of those phases. What state does it occur? And next, the relative quantities of each phase, right? So reading a phase diagram will also tell what phase transformation. So at this point, what is the phase transformation does it occur? Huh?
Liquid gas.
So this what sort of phase transformations that we can expect when we change one or more parameters of the system. So here, what are the two parameters that we are going to change? Since it is one component system.
Temperature and pressure. Temperature
Yes,
and pressure.
temperature and pressure. That is because we have only one component. So can it occur composition? එක component එකක් තිබෙනවම can we say the composition of that system? No, you have only these two variables. Temperature and pressure are the two variables for a one component system. Clear? Is it clear?
Yes,
Is
ma'am.
it clear, everyone? Okay. Right. So let's move forward. Okay. So in your session one, what do you have? The phase rule and one component system. So here I will give you the brief introduction about each and every session, right? So in session one, you have the phase rule and the one component system. So what is phase rule? So the Gibbs phase rule is an important tool used for the quantitative treatment of the system. So by looking at this phase diagram, we can say what sort of phases and what are the quantities, relative quantities of the each phase, right? However, you can determine quantitatively, that means the number, treatment of system in equilibrium. It enables us to predict the conditions that must be specified for a system to exhibit equilibrium. So two or more different phases are present in equilibrium. What sort of system is that? If it is two or more phases are there?
Heterogeneous system.
Heterogeneous system, right? If it is a single phase is occur, homogeneous system.
Homogeneous.
Yes. So such systems are studied by the phase rule. So using the phase rule, we can study the heterogeneous systems, right? So this rule predicts qualitatively the effect of temperature, pressure, and concentration on heterogeneous equilibrium, right? So what is the phase rule? So this is very important. The phase rule is this. You should know how to apply the phase rule and what sort of ideas you can get using the phase rule, right? So what is this? So phase rule is, so you can remember this, F is equal C minus P plus 2, right? So what is C? F,
Degree of freedom.
degree of freedom. So what is C?
Component. Number of
Number of
components.
components, right? What is P?
Number of phases.
Number of phases, right? So where these three variables related to the equation F is equal C minus P plus 2, right? So this is another way. So for me, the familiar way is F is equal C minus P plus 2. So the degrees of freedom, what is the degrees of freedom? That is very important terminology, which represent the environmental conditions. So what are the environmental conditions that we can use? It can be temperature, pressure, and even mole fraction. So we can change those environmental conditions which can be independently varied, right? Without changing the number of phases in the system, right? So that is the degrees of freedom. F is called the environmental conditions which can be independently varied, right? Without changing the number of phases. So here in this system, the water, one component system, right? So this we need how many, let's apply the phase rule to this, right? Okay, so here,
Madam,
apply
can you
phase,
say it again? Environmental condition which
yeah,
can independently vary
varies without
without,
changing the phase, number of phases, right?
yeah,
So that is
we call it as degree of freedom.
degrees of freedom, right? So let's now see, calculate the degrees of freedom here. F is equal, see how many number of components you have?
One.
You have only one. You have only water. So C minus P. How many phases you have here?
Three phases.
Mithana 3 phases තියෙනවද? At this point, I'm considering this
One.
point.
One.
You have only one phase plus 2, right? So what is the value? F is equal 2, right? So that means you need 2 degrees of freedom to explain this position without changing the number of phases. So what are those 2 variables? Temperature and pressure, right? So consider this point. Right? So consider this point. So let's use the yellow color. Oh, yeah. Consider this point. So how many phases you have here? Well, let's calculate the degrees
Two.
of freedom. F is equal component. How many components you have?
One.
You have only water. You don't want beyond that. You have the one component system. So the number of component is 1 here, right? right? Okay. So how many components you have here? One component system, right? How many phases you have here?
Two.
Two phases. Because when it comes to from liquid to the first gas phase appears here, right? So that means you have two phases on top of these three lines. You have two phases, right? So minus 2 plus 2, right? So what is F?
1.
1. So that means to describe this point without changing the number of phases here, you need only 1 degrees of freedom to explain this system clearly. That means you are going to keep one condition constant and varying the other condition. Keeping the temperature constant, changing the pressure, right? So that's how you can calculate. So what is this point? This is an important point for you, right? So what is this point called? Huh?
Triple point.
Yes, we call this point as triple point. So that means all three phases are in one equilibrium. You have solid, liquid, and vapor. All three phases are in one equilibrium. Clear? So all three together. So how many phases you have here?
3.
F is equal number of components 1 minus 3 plus 2. So what is the value?
0.
0, right? So that means the triple point, you don't want any degrees of freedom or the environmental conditions. You independently, you don't want change. That means the degrees of freedom 0, right here. So that's how you can calculate the using the phase diagram and the phase rule to calculate what sort of degrees of freedom the quantitatively you can calculate. Is it clear? So let's see further so you will understand then. Right. Okay. Right. So now let's see the phase. Phase is a form. I have already explained you what is a phase. A uniform system throughout the chemical and physical status. So here, a system containing only liquid water. So you have liquid water only. So what is the number of phases? How many phases are there?
1.
1.
You have only liquid water. So one phase system. A system containing liquid water and water vapor.
2.
Two phase system, right? So how many components you have here?
1.
1.
You have only one component. Very good. A system containing liquid water, water vapor, solid ice at triple point. So how many phases you have?
3 phases.
Three phases at triple point. And pure substance, if it is pure solid, it can be pure liquid and pure gas, made up of one chemical species or one phase system, because you have only solid phase, you have only liquid or gas phase, right? So that is a one component system, right? So what is a component? So here is defined as the minimum number of independent variable constituents. So for example, a liquid water. So how many minimum number of independent constituents there. Or you have only H2O. So the constituent is similar, by means which the composition each can express in forms of chemical equation. So consider water system. You have three phases: liquid, ice, water, and vapor. So the chemical composition of all three phases, what is the chemical composition? You have only water. So the number of component is 1 there. And sulfur, you know, it has 4 phases. What are those 4 phases? There can be rhombic, monoclinic, liquid, and vapor. But the chemically, you have only sulfur there. So how many components you have?
1 component.
1 component and 4 phases. Right? Is it clear? So try to understand these basics very clearly. Then only you will get very clear knowledge about the further advanced stuff, right? Okay. So now the degrees of freedom. Degree of freedom is defined as the minimum number of independent variable factors such as temperature, pressure, concentration, or the mole fraction. So this comes to the picture when the 2 component systems are being considered. Harida, concentration or composition comes to the picture. 2 component or 3 component, more than 2 component system. For a 1 component system, you don't have this variable. Clear? Is it clear? Is it clear?
Yes, ma'am.
Okay, so which must be fixed in order to define the system completely? Right? So be fixed in order to define the system completely. So system having, so you can calculate the degrees of freedom, F, right? If F is 0, it can have 1, 2, 3 or 0 degrees of freedom, right? So if it is 1, the system called univariant system. If it is 2, bivariant system. If it is 3, trivariant system. Or if it is 0, non-variant system. Or we call it as invariant system as well. Right? So if the degrees of freedom depend on the degrees of freedom, you can classify the system univariant, bivariant, trivariant, and non-variant or invariant systems respectively. So consider the following equilibrium: ice, water, vapor. So how many phases you have?
1,
Phases,
3,
3.
you have 3 phases. How many components you have?
1
One.
component.
1,
You have only 1 component. Don't mix it up. Component and phases. Phases කියලා කියන්නේ අපේ state එක solid ද liquid ද gases ද, right? Will be in equilibrium. So in triple point, right? So at triple point, you have all 3 phases are together. So in equilibrium only at a particular temperature and pressure. Hence this system, so when we calculate the triple point, what is F value? We got
0.
0, right? So that means it is non-variant or invariant system. So system does not have any degrees of freedom. So it is called non-variant, zero variant or invariant system. Right? So that is how we can classify the system. So when it comes to the explanation, you might have questions with you have given a univariant system with one component system, right? So that means you should know univariant now, F is equal 1, right? And if it is a one component system, that means you have only one component in your system, right? Okay, so these terminologies are very important. Right. So the one component system, from mathematically, you can calculate the number of degrees of freedom if P is equal 1. Can you all remember we have studied? Mangai Karanyane, all these domains you have only one phasor, right? So there you can apply the phase rule. You will get F is equal 2. That means all one component system can be completely. So what is the highest value of F we got? Huh? For a one component system? 2. So here you have, right? See, here you have F is equal to, F is equal to, F is equal to. And on top of this line, limits, F is equal 1. Here F is equal 0,
0.
right? So that means the highest number of degrees of freedom you got is F is equal 2. That means by using these two variables. So what are those two variables? The degrees of freedom 2 means you have two variables. You can define the system completely, right? Graphically by stating only two variables. So what are those two variables? Pressure and temperature. So that's why the one component system, you draw the phase diagram, pressure versus temperature. Clear
Yes, madam.
clear? Right. On appropriate axes, right? Okay. So let's move further down. Okay, so now the phase what system? It is one component system, right? So water exists in three possible phases: solid, liquid, vapor. So these three phases may form four possible equilibria. So what are the four possible equilibria the solid, liquid and vapor phases can have? Solid liquid equilibria. There can be liquid vapor equilibria and solid vapor equilibria. Solid, liquid and vapor equilibria. So these are the four possible ways of equilibria, right? So depend on that, you can. So this is a complete representation of one component phase diagram for water, right? So this means here you have ice, solid, liquid water, right? And water vapor. So here, see, at higher temperature, Mebalan, when increasing the temperature, you have more vapor, right? And if we, what will happen? So here, solid to liquid equilibria. So this is called the fusion curve, right? And So what is this one? Solid vapor equilibria? Huh? What is this curve?
Sublimation.
Sublimation curve, right? And here you have vaporization, the vapor curve, right? And where liquid water equilibria, right? So you should be able to, when you go to the upcountry, so what is the boiling point of water? What will happen to the boiling point of water?
Decrease.
It can be reduced.
Reduce. Can you explain it by using this diagram? Yes, you should be able to explain. So why?
When atmospheric pressure increases, it will reduce.
Yes. So when you go up country, so the atmospheric pressure changes, right? So that leads to, earlier you have the water vaporize at this point, at the 1 atm pressure, right? However, when you go up country, what will happen to the pressure?
Pressure decrease.
Pressure is going to down.
Pressure decreases. So that means you are somewhere here at low pressure. Less than 1 atm. So low pressure means, so you are somewhere here. So that means you will get a lower temperature at which it boils water, right? So here, the system, when it comes to the 1 atm, so what is the boiling point of water is 100, right? However, at low pressure than that, you will get a low temperature. Is it clear?
Yes, ma'am.
Okay. All right. So I'm not going to go into detail, right? The vapor pressure curve of water. So you all know OA. OA is the vaporization. Start from the point. So what is the freezing point of water under this pressure? And so likewise, you can, by looking at the phase diagram, you can explain very well the system. And with its conditions, right? So the, okay. So the water vapor system is univariant system. Why is that? Univariant system kya? So
Degree
curve
of freedom
OA.
is 1.
Yes, degree of freedom is 1. So here OA on top. So on this line, the limit, at this limit, limits of stability, all three lines, on top of that line, you have univariant system. That means degrees of freedom is 1. Clear the? Okay. So
Madam,
now
can
in
you
your,
say it again, madam?
yeah, I have explained you these things, right? So the degrees of freedom 1 on top of these lines. May lines uda. How many components you have? One
One.
component, 2
1.
phases. Then apply the phase rule is equal to 1. That means these lines are univariant systems. Is it clear? Univariant kya hai? Degrees of freedom 1. Right? Is it clear? Is it
Yes,
clear
ma'am.
now? The curve
Yes, ma'am.
OA slants upward. It slants upward and slopes away from the temperature axis, from the phase rule. So that means it's a univariant. The water vapor system is a univariant. That means F is equal 1. Okay. So now in your second session, so what do you have? Phase diagram for two-component system. So when it comes to the two-component system, in addition to the temperature, pressure, so what is another variable you can have? The composition, right? Because you have two components, A and B, right? Give me 1 second. Right? Okay. So in what will happen when it comes to the two-component system? In two-component system with P is equal 1. That means number of phases 1. The number of degrees of freedom. So let's calculate this. Clearly get this point. So when you apply the phase rule to two-component system, F is equal C minus P plus 2, right? So here what is C? If the two-component system,
Two.
No.
Two.
huh? How many? C is equal to
Two. Two.
2
No.
because you have given a two-component system. Number of phases, assume it is 1, right? Plus 2. So what is the value you got?
3.
3.
3.
You got 3. So that means for two-component system, you need to have 3 degrees of freedom or 3 variables to explain the system very clearly, right? So what are those 3 components? It can be pressure, temperature, in addition to that, the composition. So these are the 3 variables that you can use to explain the system in two-component system. Is it clear?
Yes, madam.
Right. So now we are going to draw the phase diagram for two-component system, right? So it should be a three-dimensional one since you have 3 variables, right? So is it easy task for you to draw it three-dimensionally? No. Therefore, what you can do, you keep either temperature or pressure constant, keeping one variable constant and you are varying the other composition, temperature or pressure versus composition of, suppose it is A and B mix each other, liquid A and liquid B mix each other, right? So you have 2 components. You are going to draw the phase diagram keeping either temperature or pressure constant, or sometimes the mole fraction can also be constant. Then you can draw temperature versus pressure. Is it clear? So in this diagram, 2 axes represent the 2 variables, right? While the third variable held constant. Now is it clear, everyone?
Yes, madam.
හරි. හැමෝටම clearද? Explain කරන්න ඕනේද ආයේ? Right. So the phase diagram can represent as pressure versus temperature, keeping the mole fraction constant. Or you can draw pressure versus composition, keeping temperature constant. or temperature versus composition, keeping pressure constant. Clear? Is it clear for everyone? හැමෝටම clearද?
Yes, madam.
Yes, ma'am.
Yes, madam.
Here, madam, C means composition, no?
C කියන්නේ C concentration or composition, right?
Okay, ma'am.
Right. Okay. So now in unit 4, so there are many important components. So now we are in the two component system. Hereafter we are considering two component system. So in two component system, you can have several types. There can we usually called it as binary system, right? Binary කියන්නේ two component, right? And there can be ideal binary, right? So we are going to draw the phase diagram for ideal binary mixture, right? So that means they behave ideally, right? Obeys the Raoult's law and Dalton's law, right? So, and even there can be non-ideal mixtures or liquids, right? It can ideal behavior can deviate. We call them as azeotropic mixtures, right? They don't behave ideally. And so we are going to study the distractional distillation for ideal mixtures and non-ideal azeotropic mixtures, right? And there's another. So this is the first one, ideal binary. And the second, we are going to study the non-ideal binary, azeotropic mixture. And thirdly, you are going to study solid-liquid equilibrium. And all these cases, liquid and liquid equilibrium, right? Methanai. However, here you have solid-liquid equilibrium, right? So there, the eutectic point comes to the picture. I'll explain you all these things. And there are partially miscible and immiscible systems, right? So these are the main parts that we are going to study in this unit, right? So these azeotropic mixtures and ideal binary mixtures, non-ideal binary mixtures, right? So you all should know very well all these terminologies. Okay. So there are variables called intensive and extensive. So what are intensive variables?
Eta does not depend on the matter.
Yes, that means they are independent of the size of the system, or it doesn't change with the size or the weight of the system, right? For example, concentration. Does it change with the concentration change whenever with the size of the system? No, right? And those are called intensive variables. Independent. Intensive variables are independent of the size. And there are extensive variables. For example, volume. Volume does not depend on the size, right? So those are called the extensive variables, right? And there's another important thing, the thermodynamics of phase equilibria. So we should know how it behaves thermodynamically, these phase changes. So to explain that, we need to know two conditions. The first one is Clapeyron equation, and the second one is Clausius-Clapeyron equation, right? So here consider this transition, alpha to beta transition, right? So the closed Clapeyron equation gives you thermodynamics. We know that for two phases to be in one equilibrium, if the two phases are in equilibrium, that means their chemical potentials, we called it as mu. Chemical potentials must be similar. Mu alpha is equal mu beta, right? So in that case, we can apply the Clapeyron equation, right? However, when it comes to the solid gas or liquid gas equilibrium transitions, right? So we know if gas is there with the solid or liquid. So the difference between the delta V is the difference in volume of the gas minus volume of solid. So when compared to the solid volume, the volume of the gas is very high. So we can approximately get this as V gas, right? So assuming the gas behaves ideally, we can substitute this V gas to ideal gas law, right? V is equal nRT over P. So after doing this, we can get the Clausius-Clapeyron equation for a ideal behaved solid gas and liquid gas transition. So this is the equation gives you the Clausius-Clapeyron equation. So right. So the further explanation is given in the book. You can refer the book for further explanation. Right? Okay. Right. Now, two component systems. So there can be ideal solutions. I told you there are two types of system. Binary or two component. Terminologies you should keep it in your mind. Binary system means two component system, right? And if it is univariant, bivariant, trivariant, and non-variant are degrees of freedom, right? And so these binary systems, the ideal binary solutions, right? So usually we called it as ideal binary mixtures, right? So what are the ideal solutions? That means when A and B mix each other, right? A liquid mixed with B liquid. So what will happen? The forces between two A molecules. So you have AA forces and you have BB forces, right? And you have newly formed AB forces, right? So for an ideal mixture, this condition can be applicable. AA forces approximately equal to AB forces and BB forces, right? So the ideal gas is one in which there is no intermolecular attraction nor repulsion, right? So ideal gas ideally when the system occurs or there exists ideal manner, that means AA forces equal AB and BB, right? So for a binary miscible, so what is the terminology? Miscible. A and B mix each other, right? No layer separation, right? Clear is it clear?
Yes.
If it is immiscible system, miscible means dissolve one another. If it is immiscible, you can have two layer separation, right? So the mole fraction of a binary mixture. And you should know the Raoult's law and Dalton's law, which obeys by ideal binary mixture, right? And temperature, vapor pressure, composition curve. So these are, we are going to study for a binary miscible systems. 1 second. Right? Okay. Right. So for an ideal characteristics of an ideal mixture, if all these attractions are same, A, B, B, there will not be any heat either evolved or absorbed. If the attractions and repulsions are similar, can there be any heat evolved or absorbed? No. That means an ideal mixtures of two liquids will have zero enthalpy. Enthalpy change for an ideal mixtures is zero. No heat evolved or absorbed. So if the temperature rises or falls, when you mix the two liquids, then the mixture is not ideal, right? If there is a temperature rise, that means exothermic. If it is lower, endothermic, right? So further, the total volume of the mixture should be equal to the sum of the volumes of. Can there be a volume change if the forces are similar? No, there cannot be. Delta V is also 0. No volume change due to the mixing. Clear the? So for an ideal gas, behave liquid, the Raoult's law can be applicable to an ideal solution. So applying the Raoult's law for mixture of liquids A and B, we have two expressions. So here you have, this is for the Raoult's law for A. What is Raoult's law? P. A is equal P naught A. So what is P naught A?
Partial pressure. Partial pressure of the gas.
No.
Vapor
Not
pressure
the
of the
clear
gas.
answer.
PA is the partial pressure and the P naught is the PO.
Yes, that is P naught A is the vapor pressure of POA. That means if you don't have any impurity with A, right? So the vapor pressure only due to A for POA. If you have impurities with A, then it can be changed. PA is the pressure, the vapor pressure of the component A in a solution is equal to vapor pressure of PO. This is PO component. You have only A. P naught A XA, right? So this is called as the Raoult's law, right? And similarly, you can write it for B, species B as well. PB is equal P naught B XB. What is XB? What is XB?
Mole fraction of
Fraction of B.
What is mole fraction?
Number of moles of B divided by number of moles of the total solution.
What is mole fraction? What is XB? Can you calculate XB?
number of moles of B over number of total mole.
Yes, XB is mole fraction of B. That means number of moles of B divided by Na plus Nb. Clear the right? So the mole fraction of XB, the vapor pressure. So these are the Raoult's law, which can be applicable for ideal behave liquids. Right. So now let's see the Dalton's law. What is Dalton's law? මොකද Dalton law එකෙන් කියන්නේ? Can you all remember? You have studied this during our A-levels.
Partial
Dalton's
pressure
law.
law.
Yes, the total pressure of the system is equal PA plus PB. Pressure due to A and pressure due to B. So the total pressure is equal this, right? So using the fact that you know XA plus XB, the mole fraction of, since you have A and B together, you have only A and B, right? So that means XA plus XB is equal either. How much? What is the value? 1.
1.
The mole fraction of A plus B, mole fraction of A plus mole fraction of B is equal 1, right? So in that case, you can write it P total is equal PA. Instead of PA, you can write using the Raoult's law. XA P naught A and PB XB P naught B. And you know XB is equal 1 minus XA. Right? So by using both Raoult's law and Dalton's law combine each other, you can get this equation for P total. The total vapor pressure is equal to P naught A, P naught B, right? So that means it is something like this. The system you have here, liquid A and B mix each other, A plus B, right? When this comes to the equilibrium, what will happen? Certain amount of A goes to the vapor phase and certain amount of B goes to the vapor phase. So this is your vapor phase, right? Clear you have here the solution. Is it clear? So at equilibrium, you can calculate this is for the solution. P total can be calculated by using, if you know the partial vapor pressure of POA, vapor pressure of POB, and mole fraction of A, and vapor pressure of POB. If you know all these things, you can calculate the total vapor pressure in the solution. Right? Clear Is it clear?
Yes, ma'am.
Right. So suppose you are going to you asked to calculate the vapor pressure of A in vapor phase. Vapor pressure of A in vapor phase. Right? So in that case, you can calculate the mole fraction of A into P total. Clear the? So this is how you can calculate the vapor pressure in the vaporous system. Right? Clear the? Make clear the හැමෝටම?
Madam, last said point is not clear. Can you tell again?
Yeah. How about others? අනිත් අයට කොහමද? Huh?
Okay, ma'am.
So, right. So, the last part is, so here you can calculate the P total by using both Raoult's law and Norton's law. Up to now, is it clear?
Yeah.
You can calculate the partial vapor pressure corresponding to this mixture, A plus B liquid solution. However, on top of that, in a closed system, you have vapor phase here, right? Which occurs due to the vaporization of A and B. A and B vaporize vela at equilibrium, it goes to the vapor phase as well. Is it clear?
Yeah.
If you ask to calculate the mole vapor pressure of A, that is PA, in vaporous area, right? So that can be calculated by using XA.
Yeah,
That
yeah.
means the mole fraction of A in vapor state into P total, right? So that means if you know the P total value and vapor pressure in the vaporous side, you can calculate the mole fraction of A in vaporous curve, right? So the vapor phase. Is it clear? Is it clear
Yes,
now?
ma'am. Yes, ma'am.
හැමෝටම clear the?
Yes.
Is it clear,
Yes, ma'am.
everyone? Okay. So there are several examples given in several papers, right? So you can do all these examples, right? Right. So now when it comes to the ideal binary, what is the meaning of binary? You have two components. Ideal, which obeys Dalton's and Raoult's law. Obeying Dalton's and Raoult's law. So that occurs. So how this phase diagram occurs? කොහොමද ඒක ආවේ? Suppose you are going to draw the phase diagram for a binary ideal mixture, A and B. Right? So here, the mole fraction of, suppose it is A, XA. The mole fraction of A. So, suppose this is the pressure, vapor pressure. Right? So, at this point, what do you have? 100% B. Clear the... At this point, what do you have?
100% A.
Huh? A the... sorry, A. Yes. 100% A here. Right? So that means on top of this line, you have POB. On top of this line, you have POA. Is it clear? Clear the...
Yeah.
Right. So that means for a pure substance, you have the pressure P naught A. The vapor pressure of B, the pure substance. So here, the vapor pressure of POA, P naught A. If the two values are given to you, PA is less than P naught A, less than P naught B කියලා දුන්නොත්, you have to draw if it behaves ideal binary mixtures now. So you should obtain your line like this. Why? What will happen? When this is 0, if you don't have any A here, so your vapor pressure due to A is 0. That means it goes until the PO P naught A, right? And starting from here, when we increasing the composition of B, you are going this way towards this side. මොකද වෙන්නේ? When you go towards this side, you are increasing B. So what will happen? When you are slowly increasing B into that. So increase the vapor pressure and it comes to the highest P naught B value. Is it clear? Clear the...
Yeah.
Hurry up quickly.
Yes.
Is it clear? හොඳට මේක ගන්න. So this obeys PA is equal P naught A XA. This line. Right? So this line is PA is equal P naught A XA. That means Dalton's law. So at this composition, you can calculate the pressure by using Dalton's law. And this curve, this line, may line that is PB equal P naught B XB. Right? So at this point, you can calculate, since you know the mole fraction, you can get the pressure value. Right? However, so when you draw a line in between these two, so that is the total vapor pressure of the system. PT is equal PA plus PB. Right? So that means you can get the, suppose at this composition, මෙන්න මේ composition එක හිතන්න. Right? So what is your PA value? So this line, මෙන්න මෙතනින් ගමු. Right? So at this composition, so what is this line?
PB.
PB.
B.
Right? So this gives you the PB value, my pressure එක. And at this composition, what is PA? This value. Right? So now what is P total? P total is this. Right? So that means this plus this මේ දෙකේ එකතුව gives you the P total. Is it clear? It obeys the Dalton's law. PT is equal PA plus PB. Is it clear? Clear the හැමෝටම?
Yes, madam.
Similarly, at this composition, this plus this gives you P total. Right? මේ දෙකේ එකතුව this value plus this value gives you P total value. Right. So when it obeys the Dalton's law, you can write this. So we'll quickly move. Right. So this is the vapor pressure versus mole fraction. However, when it comes to the boiling point, the temperature versus mole fraction, unlike the vapor pressure වගේ නෙමෙයි, it does not obey linearly. Right? So this line not obeys linear manner when it comes to the boiling point. So repeating the process of considering the vapor and then reheating the condensation boiling point, you will eventually get POB. That means the boiling point versus composition phase diagram. So earlier we have drawn pressure versus mole fraction phase diagram, right? However, when it comes to the boiling point versus the mole fraction, it gives you something like this, right? So here, clearly try to understand this. Now the temperature here, at higher temperature. So here you are considering the liquid vapor equilibrium, right? මොනවද අපි consider කරන්නේ? Liquid and vapor equilibrium, right? So you have here the closed system, you have liquid mixing binary mixtures, A plus B, right? And here you have vapor phase. So you are studying here the liquid vapor equilibrium. Is it clear there? Make it clear there. Is it clear, everyone?
Yes, madam.
Right. So you are studying the liquid vapor equilibrium. Binary, ideal binary solutions. Right? So at higher temperature, what do you have? Liquid the vapor the.
Vapor.
When we increase the temperature, you have vapor here. And at low temperatures, you have liquid. However, in between, you have both liquid and vapor. Liquid and vapor both are there. Right? So, how many phases are there in this? මෙතන කීයක් තියනවද? You
One.
have only one phase. What is that phase?
Liquid phase.
Liquid phase. How many components you have?
Two.
Yes, very good. You have two component systems, right? However, on top of this line, how many components you have? And on top
One.
of this line,
One.
One.
You have only one component because you have POA or POB, right? In between these two lines, you have two components. A mix each other, A mix with B or the other way, right? So therefore, carefully and try to understand you have one component, two components here and sorry, not two components. It has to be one because you have only PO, one substance. And how many? Yes, one component on top of this, right? So here, how many phases you have?
Two.
Huh?
Two.
Phases, two. How many components?
Two.
In between
Two.
two, right? So can you add the phase rule? And also here P is equal 1 and F is equal, C is equal 2, right? Clear there? Right. So now you should be able to apply the phase rule each and every place. Method phase rule එක දාන්න. F කීයද? F is equal C minus P plus 2. 2 minus 1 plus 2. Here kenawada?
Yeah. Three.
3. Right? And here 2 minus 2 plus 2. F
Two.
kiyada?
Two.
F is equal 2. And again here F is equal 3. Right? So that means by using this 2 degrees of freedom, you can explain this area, right? So there can be 2 degrees of freedom, right? So let's try to understand the distillation, steam distillation or the fractional distillation to separate out A and B. Right. So fractional distillation of ideal binary solutions. Then, so how do you do? What is fractional distillation? Can you all remember this setup? The fractional distillation setup. So this is the one. So you have A plus B solution here. So you are going to heat this. So what will happen? So your vapor, when it comes to the mixture boils at lower temperature than both POA and POB. මේ mixture එක නටන්නේ boil වෙන්නේ at lower temperature compared to T naught A and T naught B දෙකටම වඩා low temperature, right? So this is called ideal binary solution, the fractional distillation, right? So this vapor goes up and it comes towards this through the condenser. What will happen? So the liquid will be collected here, right? Clear? Is it clear now? right? So, okay, now we are going to do the fractional distillation, right? So, consider the composition of C1 that is rich with B. Sorry, rich with A, because you are mole fraction of A towards this. So, this composition is rich with A and you have this much of B. So, you are going to take this composition and increase its temperature, right? So, at this point, the first, what will happen? So, this is the composition. This is we called as liquidus curve. The liquid composition gives you by using this. And this is the vaporous curve. That means the vapor composition can be using at this curve, right? So what is this? So we can use this liquid solution, liquid composition having the C1 composition. And what are we going to do? No, let's start from this end. Yeah, C2 composition. Get the solution with C2 composition. So this is you have liquid, right? So keep that into the fractional distillation, the round bottom flask, right? And then increase its temperature. What will happen? You will get the vapor out, right? So that vapor can be collected and get its liquid, right? So this can be collected, right? And you will be collecting the mixture of this, right? And again, increase its temperature and get the vapor composition and collect its liquid. And likewise, you will be ended up with POA from this side, right? And if you will do the fractional distillation starting from this end, you will ended up with POB from this end, right? That means after the fractional distillation of ideal binary mixed solutions, you can separate out POA and POB from fractional distillation. So the POA goes to this flask and POA remains here, right? So that is the fractional distillation for ideal binary mixture, right? So try to understand. It's everything is given in your book, right? Now let's quickly go. So now the non-ideal mixture, right? So earlier, can you remember for a ideal solution, it obeys the Raoult's law and Dalton's law. However, for non-ideal mixture, it deviates from the Raoult's law and Dalton's law. So there can be positive deviation or there can be negative deviations like this, right? Clear it's unlike the vapor pressure mole fraction. Can you all remember for a non-ideal binary mixture, we obtain a linear curve like this. Can you remember? However, for a non-ideal mixture, it won't obey a linear way. You will get either positive deviation or negative deviation from ideal conditions. So the real solutions show deviation from Raoult's law and Dalton's law. Consequently, the vapor pressure calculated based on these laws will be different from the actual values. So the positive deviations or negative deviations. Clear? Right. So there can be very large positive and very large negative. So remember that the pressure versus composition, if it is this up, we called it as positive deviation. However, when it comes to temperature versus mole fraction උනොත් කොහොමද වෙන්නේ? මේක temperature උනොත් pressure වැඩි වෙනකොට temperature අඩු වෙනවා. So that should be this type of one. Clear the? Is it clear?
Yes, madam.
However, the positive deviation using the pressure versus mole fraction curve again. And pressure versus mole fraction, if it is the downward, it's negative deviation. So similarly, the temperature versus mole fraction is upwards. Right? So what is positive deviation? That means A-B interactions are loosely bound compared to AA and BB interactions. Right? So when it bounds loosely, it can very easily break and increase the vapor pressure. Right? Is it clear? A-B interactions are new interactions. AA and AB means, sorry, BB means existing one. Compared to the existing bonds, this has the lesser strength. That means very easily can be break down and goes to the vapor phase. So that's why you obtain a positive deviation. If it is higher, that is negative deviation. Is it clear? Right. Okay. Moving down, right? Okay. And then we come to the non-ideal binary mixtures. We call them as azeotropic mixtures. What are those? Huh? මොනවද අපි මේවට කියන්නේ?
Azeotropic.
Azeotropic mixtures, non-ideally behaved mixtures, right? So that can have negative points, or there can be some can have positive points as well, right? So this is a boiling point versus composition. Boiling point versus composition for the ethanol water system. Ethanol and water system, an azeotropic mixture. That means the azeotropes. So what is azeotropic mixture? In this case of mixtures, ethanol and water, it occurs a minimum at 95.6 by mass of ethanol in the mixture, right? So the temperature of this composition comes to the minimum value, right? At 95.6%. That means this value. Minimum value. Ethanol 95.6 plus water remaining water. At this point, it forms a minimum value occurs, right? So the boiling point of this mixture is, what is the value? What is the boiling point? Huh?
78.2.
78.2. Compared with the boiling, what is the boiling point of pure ethanol? So here you have pure ethanol, 100% ethanol. What is the boiling point?
78.5.
78.5.
0.5. However, when they mix each other, water and ethanol, it gives you a lower, a minimum temperature at which it boils little less temperature compared to the pure ethanol. Is it clear? So that's called, it don't behave ideally, it behaves non-ideal way. Non-ideal binary mixture, right? So compared with the boiling point of pure ethanol, and the boiling point of water is 100. Boiling point of pure ethanol is 78.5. However, the mixture of ethanol and water boils at lower temperature compared to pure ethanol and pure water. So what is that value? 78.2. Clear the mixture එක boil වෙන්නේ මේ දෙන්නගෙම temperature එකට වඩා අඩු temperature එකකදී. Right? 78.2. So this is non-ideal azeotropic mixtures with a minimum. And there are mixtures, you can have azeotropic mixtures with a maxima. This is similar, right? Right. So now let's see the fractional distillation of this type of system. So this is your liquidus curve. This is the vaporous curve. Right? Take this composition. Temperature එක වැඩි කරගෙන යාම, you have the liquid composition here. So you collect the vapor composition the other side and decrease its temperature. Get the liquid having C2 composition. And again, collect its vapor. And you are here. So at the end, you will ended up with here. Can you go beyond this point? Huh? Can you go beyond this point? For azeotropic mixture? Huh? If this is the fractional distillation is being carried out, can you go beyond this point? Oh, can everyone hear me?
Yeah.
Is it clear? Or you need again explain this? Huh?
Why, madam, we can't go beyond that?
Why? Here? Because you will do the fractional distillation, collect the liquid and get its vapor and reduce its temperature, condensation, and collect this C2. And like this, the fractional distillation being carried out, and you cannot go beyond this because it destruct here. From this point onwards, you cannot do freshly the fractional distillation. Right? So that means, and from this end, you will get pure water. And this end, you will get azeotropic mixture. And do now the fractional distillation from this end. Collect it and do it like this. So you will end up with pure ethanol. And this side, you will finish. You cannot go beyond this. So that means when a non-ideal binary mixture, when it fractional distillate, you can get either POA or POB with azeotropic mixture. Is it clear?
Yes.
Is it? Everyone?
Yes, madam.
Right. So similarly, so ethanol water mixture, it has, almost very much similar. 78.52 here, 78.5 here. The difference is very little. However, there can be the huge difference between these two as well. There are systems, right? So this is again, do the fractional distillation. You cannot go beyond this because it's break here. There's a break here, right? At the azeotropic condition. So you will get either POA or POB with azeotropic mixture. When you start do the fractional distillation from this end, you will end up with azeotropic mixture and POB. And when you do it this way, this side, you will end up with POA and azeotropic mixture. Is it clear?
Yes, madam.
Right. So it is impossible to get pure ethanol by distilling any mixture of ethanol water. Can we collect both POA and pure ethanol and pure water from by fractional distillation of ethanol water mixture?
Can't.
No,
No.
we never cannot get both together. Either POA with azeotropic mixture or POB with azeotropic mixture. Right? So we have here the constant boiling. We call them as constant boiling mixtures or azeotropic mixtures, where the vapor composition is exactly same as the liquid. So when it comes to this, here at this point, what will happen? This is at this point, you have both your vapor and liquid. දෙන්නටම තියෙන්නේ the same boiling point. So unlike these conditions, so when you consider this condition, this composition, you have, this is your liquidus curve having this temperature, liquid is at this temperature, and your vapor is at this temperature. However, at the azeotropic point, at this point, you will have a constant boiling mixture කියන්නේ එකයි. The boiling point of the vapor is exactly same as the liquid. Right? So that's why we called as constant boiling mixture. So the azeotrop occurs ethanol water mixture 95.6. Is it clear?
Yeah, madam.
We have some more to do. So before the CAT exam, right, we will have another extra day school on 1st of October, right? So there we will be able to discuss some questions, right? Haridha?
We have 26th as well, no, madam?
Yes, 26th we are going to cover unit 3, no?
Okay, madam.
Right? 1st of October before the CAT 2, we will discuss few questions, right? On 1st of October, you have another extra day school now. We will discuss past paper questions. Enisa, by that time, you should get ready for the for everything. Question karanna. Hari? So now I'm going to do the theory, mainly theory, right? So try to understand this very carefully. So this
Madam,
is about
1st of October, I don't know whether I can join because of I have to consult a doctor at that time. So are you going to upload the
ma'am.
recording?
Yes, I'm going to upload the recording. It doesn't matter, right? You can go through the recording and try to understand, right? So just 1 hour time for
Okay,
me
madam.
to discuss questions, right? And next, the second 1 hour will be given to unit 3, right? Okay, so now this relation I'm not going to cover again, right? Medical monkey because I have already explained. Right, distillation of non-ideal, again I have explained, right? So try to understand by looking at the slide, right?
Madam, do you upload this presentation?
Huh?
Upload this presentation?
Yes, I'm going to upload it, right? So you can go through.
Madam, 26th also, can we take this time duration 6 to 8?
No, it's the scheduled time. We should go with that, right? Otherwise, it will be a problem. There will be clashes for the others. 1 to 3 we have, right? So if you all
Okay,
are
madam.
going to miss this, you can go through the recording, right? So because we cannot deviate from the scheduled time, that is because there will be clashes with others, right? Okay. So now the solid liquid, then mixture liquid equilibrium, liquid vapor equilibrium. Calling liquid and vapor at equilibrium. Now we are going to study the solid vapor, solid liquid equilibrium, right? Okay, so there I'll just briefly tell you few things. So again, it is two component system. Eutectic temperature and the composition are new terminologies when it comes to the solid liquid equilibrium. So what is eutectic? So let me explain using the diagram. Right. So this is the one. Two component simple eutectic mixture. Right. And this at temperature versus small fraction of B. Here you have XB1. That means 100% B on top of this line. 100% A here. Right? Here you will get, you can do it experimentally starting from 100% A and add little amount of B into the sample. Then you can get the temperature at which the first liquid, the first solid particle appears, right? So that means at higher temperature, you have liquid. At low temperature, you have solid, right? So in between, this is the line, right? So when you do a experiment, you can obtain this type of curve, right? So this is for the starting from POA and adding B into this. So there should be a temperature at which a lowest temperature at which this gets solidifies the liquid directly gives you solid A and solid B. However, in between these lines, what do you have? Liquid plus solid A. Because this end, you have 100% A. Right? So this area rich in A solid. So suppose you are starting from somewhere here, this point. You have the composition line is this. Composition is this. That means you have rich in A of that particular liquid composition. So slowly decrease the temperature, right? So at this point on top, on this line, right? So we'll go to this, slowly decrease temperature. And at this point, the first solid A particle appear. And after that, that's why during this area, you have solid A plus liquid. And again, you decrease the temperature. At this point, both solid A and solid B also get solidified. So that's why, and in this area, you have both solid A and B. Clear the, is it clear?
Yes, madam.
Right? Alright. So starting from this end. Now let's start from this end. You have the composition, this composition having liquid. So slowly decrease temperature. At this point, the first solid mono particle ekada?
B.
B. Because this area B is rich. Right? So the first solid B particle appears. That means in this area you have liquid and solid B. And further down, decreasing temperature. At this point, you can obtain the first solid A particle as well. Right? So that means in this area, May area, okay, you have solid A plus solid B. Both are solids. Can they mix each other? A solid dekai, B solid dekai, they are separately solidified. So how many phases you have here?
1.
No, it's not
Two
one.
phases.
You have 2 phases. That is because solid A separately solidified and you have another solid phase. 2 solid phases. So number of phases there is 2. Clear the? Right. So likewise, this point is called the eutectic point. The lowest temperature at which the liquid and both solid, methanol, there's a 2 solids, solid A and solid B are in one equilibrium, right? So liquid and solid A and solid B are in equilibrium. Clear? That is the lowest temperature at which all three are in one equilibrium. Right. So you try to read the book very carefully and understand it further. Eutectic temperature. We call this as eutectic temperature, right? So this is the eutectic temperature, minimum temperature, and this is your eutectic composition. Right. Right. So you read this further. Yeah. So this antimony and lead behaves similar way, eutectic type composition, right? So this is the curve. You can obtain this and this. So this is the lowest temperature at which all three liquid and solid antimony, solid lead are in one equilibrium. Okay. So this is the temperature versus mole fraction of lead, right? And constant pressure. And there can be isothermal. That means constant temperature behaviors as well. Right? Okay. Right. So what are cooling curves? Cooling curves කියන්නේ we are going to analyze, thermal analysis is going to do. Right? So starting from this, consider this line. So you are going to draw the cooling curve for this particular system. Right? So to draw the cooling curve, you have to calculate the degrees of freedom, right? For that, here you have one phase. How many components?
2.
2 components. C minus P plus 2, 2 minus 1 plus 2 equal 3 here. However, you kept one of these variables constant. මොකක්ද ඒ constant තියාගත්ත variable එක? Temperature versus mole fraction. Phase diagram. Pressure is constant, right? So here you will get if tonight but since pressure is constant, so you will get F is equal to here. Is it clear? That is because pressure is constant, right? And at this point, the first solid antimony particle appears. How many phases?
2.
Solid antimony and liquid. 2 phases. How many components? 2 components. 2 minus 2 plus 2. Here then 2 Na. F is equal 2 here. However, since the pressure constant, exactly the F is value is 1 here. Right? And now apply the phase rule to this. At this point, how many phases? Sorry. At this point, may point again. How many phases you have?
2. 2. 2.
Huh?
3, right?
Very good. You have 3 phases. What are these 3 phases?
Antimony,
Liquid.
lead, and
Very good. Antimony, solid lead, and liquid. So you have 3 phases at this point. May own eutectic point condition again. So at eutectic temperature, you have 3 components. 3 phases and 2 components. 2 minus 3 plus 2. සිය දෙන්නේ. මෙතන F1 කියලා ආවට you kept pressure constant F is equal 0. Right? And at this point, F kiyada? Solid antimony plus solid lead. Number of phases 2, components 2, 2 minus 2 plus 2, 2. Since pressure constant F is equal 1.
1.
Right. So you can use these values. F is equal to now. Your cooling curve is temperature versus time. With time, you are going to draw the cooling curve. Right? If the kind your cooling curve should be a curve like this. If F is equal 1, it should be a straight line like this. Again, decreasing. And if F is equal 0 at the eutectic condition, temperature, so you will get a line parallel to the x-axis, F0 කොට. F is equal 2 here, F is equal 1 here, F is equal 0 now, you will get a line parallel to this. And again here, F is equal 1. That means a straight line like this. මේ වගේ straight line එකක්. Similarly. Right? Clear the? So likewise, you can draw the cooling curve. We call this as cooling curve at this composition. මෙන්න මේ composition එකේ. So similarly, try to understand these try to draw the cooling curve at this point, and on top of this line, the difference is number of component 1 here. Clear? Harida, is it clear? Usually if දෙක වුණොත්, it's curved like this. If F is equal 1, it's a straight line. If F is equal 0, that means parallel to x-axis. Again, F is equal 1. Right? Okay. So try to understand these things. Right? So you might not be able to grasp everything. Right? තනියෙන් පොත බලලා try කරන්න, study කරන්න. Right? If not, you can ask anything you wanted to clarify. You can come and meet me when I'm free time. I'm having a free time, right? Okay. So this is the cooling curves. So මේ බලන්න මේ පොතේ ඇඳලා තියෙන diagram එකේ. So this cooling curve is for A. It is something like this. A කියන්නේ මෙන්න මේ point එකේ cooling curve එක ඇඳලා. Right? This corresponds to F0, F1. At this point, මෙන්න මේ composition එකට ඇඳලා. Right? So likewise, so the B is similar to A වගේම මේ විදිහටම එන්නේ. Right? And C point එකේ it is different. Right? C is different. Co-C. C ඇඳලා බලන්න. Only difference is you have here liquid only. At this point, you will get 3 phases. And at this point, you will get 2 phases. Right? So you can draw the cooling curves at each and every these compositions. Right. මේ මම ඇඳලා තියෙන්නේ. So these are the cooling curves. Right? මේවා එනවද කියලා try කරලා බලන්න. So this is the cooling curve for pure lead. And this is the cooling curve tin lead eutectic mixture. Now see, try to draw the cooling curve for eutectic mixture, right? මෙන්න මෙතන mixture එකට cooling curve, try to draw it. And for the eutectic composition cooling curve. So both these are very much similar, right? Something like this. මේ බලන්න. So these two are very much similar. This one and this is the cooling curve for eutectic composition. It is very much similar cooling curves. However, in between these two, you will get this type of cooling curve. The කියලා දීපු විදිහට. So this is F is equal to නම් මේ shape එකෙන් 1, 0, 1. Right? Clear the right. You try to draw it by yourself, right? Okay. So lead and silver and lead also behave similarly. Right. So there are certain make among incongruent. I'm not going to go into detail. There are certain compounds when they mix each other, they form incongruent melting and concurrent melting points. Concurrent melting කියන්නේ during the melting of a compound, it forms many type of compound. Right? So this is the maximum time. So if you have a concurrent melting, this is the concurrent melting mixture, right? So two eutectic points දෙකක් එකට එකතු කරා වගේ graphs. This is one eutectic composition. මේ කලින් අපි study කරා වගේ. This diagram මෙන්න මේ part එක, and this gives you another eutectic composition එකක් මේ here. So for a given two eutectic point, you can have one concurrent, 2 minus 1 always. If you have three eutectic, right? Three eutectic තුනක් තියෙනවා කියන්නේ. How many concurrent?
2.
3 minus 2. Clear? Sorry. 3 minus 1. හැම වෙලාවෙම එකක් අඩුවෙන්. These are the eutectic composition. තුනක් තියෙනවා. Then you have two concurrent melting points, right? So that you can study, right? Further, it is very much similar to what we have studied. අපි කරා වගේම දෙකක් එකට වගේ. See, this is one eutectic point. මේ point එක. There's another eutectic. මේ side එක. දෙකක් එකට එකතු කළා වගේ. Right? So this is the concurrent melting point. ඒ කියන්නේ melting solid phase melt to a liquid within the same composition as the liquid phase. So this melts with the same composition as the liquids. That is called the concurrent melting point. Right? Okay. The solid liquid mixtures may අපි study කරන්නේ. Right. This is another example, the solid liquid mixtures. Yeah. So these incongruent melting, try to understand this, right? So there can be, when they mix each other, there can be incongruent melting. Melting, the solid phase melts to a liquid with a composition different from the original solid, right? So I'll explain, try to understand this. It's clearly mentioned in the book, right? Okay. And session 6, you will have the partially miscible and immiscible systems, right? Partially miscible or immiscible, you can have 2-layer separation, right? If it is immiscible now, so in that case, what sort of phase diagrams can it occur, right? I think, so you try to understand these phase diagrams for a partially miscible and partially miscible kyanne or immiscible, you can have 2 phases, right? So in this case, you are having A plus B, right? 2 liquids, A and B, when they mix each other, they form a layer separation, right? So consider this temperature, right? When temperature when you let's consider the mole fraction, right? So when you consider the mole fraction, yeah, let's see like this. So you consider this. You have here මොනවද තියෙන්නේ? POA, right? Add little b into A. Then there will be a layer separation. 2 layers will form at this point. And after that, you will have 2 layers in between these two until this point. However, when more and more B is adding, it goes to and again 1 layer. So in between these, you have heterogeneous 2 phases. However, all these areas, you have 1 homogeneous 1 phase. Clear? So consider another temperature. At higher temperature, temperature increase karnakotta, when we add B into A, so the layer separation occurs at little higher composition than this. Okay? So likewise, when you again increase temperature, composition is this. And there's a maximum temperature at which we can go for the layer separation. So that is the mole fraction of this. And after that, beyond this temperature, may temperature ekata udding, you cannot have any layer separation, right? So when we increase the temperature, this will make a fully miscible type 1 beyond this temperature. So that is called upper critical temperature, right? And there are lower critical temperature composition diagrams as well, right? Okay. So right? So these are the maximum, the upper critical values, UCT, upper critical temperature, and LCT are these. When they mix each other, they form a lower critical temperature, right? Okay. So that's all I wanted to, I'm trying to give you the maximum, right? So try to understand after reading the book carefully. You have
Madam,
any questions? Yeah.
madam, in this one, how when the temperature is decreasing, it becomes homogeneous. Is it?
Yeah. So you mean the lower critical conditions?
Yeah.
So that means at low temperature, it forms homogeneous. However, when increasing temperature, it tries to form 2 layers,
Heterogeneous.
right? The other way.
However, madam, when the temperature increases, the solubility will increase, no?
Yeah, there are conditions, there are systems which does not occur the same situation, right?
Wow.
At lower temperatures, they form homogeneous, right? Fully miscible systems at low temperatures, right? What is
Okay.
that? At low,
Yeah.
low temperatures, you can have homogeneous. This is the lower critical temperature, right?
Okay, madam.
Okay. So now I'm going to stop from here, right? So if you have any more things to clarify, you can come and meet me, right? So try to study the book, course material. Everything is there. Hari? Okay, do you have any questions? I will share the presentation.
Madam, can you share the presentation into the Telegram group after this lecture?
Yeah, I can send you the recording as well as the presentation. Right? Harida? Okay, I will stop from here. So, did you learn something new?
Yes.
Madam.
So,
Yes.
now with this little knowledge, you can go beyond after reading your book, right? Okay, good luck for the second cat. We will meet on 1st of October to do certain questions, right?
Madam, can you upload now into the Telegram group?
Uh, you mean the presentation?
Yeah, on the presentation.
No, I can upload it with the recording, right? So it will take little time. Tonight I'll try my best to upload, right? So
Okay,
because it
madam.
should convert into the normal way, no? Right? I will upload as soon as possible. You try to read the book and understand. Are
Okay, ma'am.
Okay. Good night.
Thank you,
Good.
madam.
Thank you, ma'am.